Hi everyone, my name is Gavin. Today's topic is called Equip Your Performance Toolbox, Cython versus Pybind11. So first thing to introduce about myself, and I'm a quantitative developer working in asset investment managers course, which is a quantitative asset management firm. In short, people call it the quant fund. And I work in an IT team, so we develop in Python, which is good. And thanks to the flat learning curve of Python, researchers research in Python. They run the Jupyter notebook, which is also good. And after the research work, we have deployed the production work, the pipelines, the data flows in Python. And so as the fund managers also use Python, so I guess this is the best world, the dreamland for Python developers. This is the only language, not English, not French, not Chinese, only Python. And for example, if my boss would like to get the coffee from me, he just write a script, import, request.get, Gavin.Chan, data equals to coffee. Then he got it. At least I told my colleagues today I will go to PyCon. They will not thought it is a mathematics conference, 3.1, 4.15 conference, is it? No, it's Python. So, but always is a concern for performance in Python, especially on CPU-bound problems. I guess for IO-bound problems, they're pretty much good libraries, solutions to solve them. But today I would like to focus more on the CPU-bound problems. I hope today I will bring you the insights that you have a bunch of tools to enhance your performance. Normally, writing C extensions is at the very bottom of your priority, but we'd like to give you insight that it is not that hard. Sometimes it's straightforward. And also, I hope that for takeaway for you guys is you can choose the proper tools when you would like to write the C extensions and know about the similarities and differences between some of the common tools. So a little bit warm up. So I illustrate, for example, to tell you why sometimes writing C extensions should be in your pocket, ready to be used. So it is an example which is commonly used in an asset management firm, which is to compute the risk exposure. For example, I have a basket of instruments like stocks, FX, interest rate products. They may have their own currency to be traded. So for example, USD or Europe. Then for the basket of investment I have to raise, it represents the investment I put in my pocket. So for example, for the first instruments, negative 0.3 means I shortened 30 cents per dollar I invest into. The objective is to compute the risk exposure for the portfolio on the currency in this part. So finally I can get USD, I short $1 per dollar I invest into. Europe, I long $1 for dollar I invest into. This is critical and always to be used because, for example, your portfolio is in Europe dollar dominant. You don't want to have the USD risk. You would like to hedge unnecessary risk as much as possible. So you have to see what kind of risk you're exposed to. So off your head, you may have a solution like this. So you iterate for each for loop for the labels you have. Then go for the basket of instruments to check which one belongs that label. Then sum up the risk exposure for that and returns the list out. A better one, maybe you have those lists in NumPy array. Then this solution will boost up your performance by two things. One is the list comprehension, which is faster than writing for loop. Second is you can see the NumPy. There's a NumPy imported. NumPy will help you to use the vectorizations to boost up your performance, which means you're running simple operations on the list of arrays, and it is running the operations in parallel for the elements inside. So in the MP-ware, it's the bracket. So first one, we check which label belongs in the instruments. For the first one, it creates a list of arrays. Then if it is true, then it goes for the arrays, otherwise to be 0. After operation, it creates another array. Then sum it up. But normally, the construction of the object or the memory allocations is the overhead of your performance. So to reduce runtime of arrays construction, in this case, you can think to use the linear algebra array to do that. So the dot product of the two vectors means the weighted sum of the labels true or false and the rays you have. Then on that, you can run in the sum on the fly to have only one time of array construction. So I benchmark a little bit. So I create a basket of 100 instruments, and then randomly assign, if I remember, it should be 5 labels in it. So the last one is the best one. So we pick out this one to compare with the furthermore examples. But you are smart enough, you're not fooled by me for my examples, because you think my previous solutions has the complexity which depends on the size of labels, but also the size of the arrays of the instruments, right? But why I have to go to that kind of complexity? I can reduce the complexity to the least of the size of the instruments only. So in this example, I just iterate through for each instrument. Then if it belongs to that label, I just sum up or add that back to the risk exposure list. But the problem comes out. So in Python, expectedly, if you have a better performance, or I would say if you have a better complexity algorithm to do it, theoretically, it should produce you a better result. So I benchmarked it with 1,000 instruments, randomly assigned different numbers of labels in it. So you will see the orange one is the better complexity, while the blue one is the worst one. But I'm not doing the apple-to-apple comparison, because my better complexity is written in Python, nothing in NumPy. But I can't think of anything which is using NumPy to do it. If you can, please tell me. So that means in this case, you're comparing two different aspects, but one with a better complexity, but using the worst library to do it. So it comes up this idea for me when I attend, I think it's a few months ago, I attend to a coding competitions. So my teammates use C++, he's doing very well for the coding competitions. I chose Python. I was very regretting on this part, because not only on the performance, but the coding competition gives you time to solve the problem on the algorithm, but not to give you time to choose which library you should use. That's the problem. C++ is simple, for loop only. So to wrap up, on the Python approach, for you to enhance the performance, go back to your Computer Science 101 class, algorithm complexity. But then it may not work. Then you will resort to use the libraries, Python libraries, NumPy, Pandas, for GPU, kubedf, so as to enhance the performance on the C API or C extension levels. Some people resort to multiprocessing, but I'm not a big fan of it. First of all, it's not usable in Windows. You can't do copy and write. And second, it makes your code a little bit dirty or ugly to read. So we got into all those considerations. So I would say, why don't we resort to the very basic? We write the C extensions. And if you compare back to Python, Python is an interpreted language that you may know. If you just compile your source code to the bytecode, we call it bytecode, but not the machine code as C++. That's why it's source node. And not compile the machine code during the runtime. You just put the bytecode in the virtual machine. That's why Python is Node, especially C Python API. While I put these two libraries to compare, I would say there are plenty of solutions to write the C extensions other than these two libraries, but I put these two to compare because Cython, which is a library, which is easy for developers, especially Python developers to use, you can have a Python-like syntax. Even though you have your Python script, you just change your extension from .py to .pyx, and then compile it via this Cython. You already gained 10 or 20% performance. And not to mention, you change a little bit to use the Cython syntax to declare the type. Pybind11 is another world, which you have your C++ source code. you need to bind your C++ functions back to the Python, the CPython API, so that the two different roles that you can use, I would say they have some contrast. And in the following slides, I will compare the similarities and difference between that. I hope you guys, after the talk, you will choose which is better case for you. First, for the building system, I would say they're roughly the same. They support most of the system you use, and you can compile it via the zap.py for your whole project. If you have a single file, you can compile it via the command line. And what is also good and important for me is I'm a Drupal notebook intensive user, so I really need the IPython magic functions. So if you have it, it means you write your piece of source code on the cell, compile it, run to compile it, and the next cell you can use it. So they both support that. While Pybind11, you need to install the external library called ipybind. To implement the functions, Pybind11, you just bind your C++ functions with your explicit Python name. While in Cython, there are several ways you can do it. 3 types. One is called def, the Python function. It means. Second is called cpdef. It means it's a function which can be accessible via the C level or in Python level. While underneath, it can call the C level functions, which is in the syntax of cdef. It supports the docstring, very important for the developers. Function overloading, there's something cool for me for Pybind11. That means you have multiple function signatures, then you can bind the same Python functions. When it's called with the argument list, it will look up in the right implementations to run on that. Also, it supports the we call the variable length arguments. So Pybind11 supports that, but in Cython only supports in Python functions. Let's have a taste on the examples of Cython. So first, we can import the C extension types from the NumPy. For the NumPy user, it's a good news. Then we can also import the NumPy module in the Python level. That means you can also call reuse the NumPy functions. And then for the functions, before going to functions, there are functions, the decorator. So I turn off the bound checking so as to, for the performance. And also I turn off the wraparound. That means you can't provide the the negative index in it to access to the array. Then I declare the cpdef. This Python functions also accessible in C level. I declare the types, and I can choose not to declare it. You can see I declare the input types, but not the output types. I can put the docstring as is the Python function. Within the scope, I declare what kind of variables and the types to use. Then, which is really good, is you can tell the guild. It means every time you just run under the scope, you don't need to get the global interpreter knock and release it. It boosts up so much for performance. But the assumption is within the scope, you have the piece of code which doesn't access to any Python object, but only on the C object. Then within, I call the C level function, which is called underscore compute label exposure. Then I implement this C level API, which is C level functions. Also declare the types and return types. I declare function as no guild. That means within the functions, always release the guild and not get it and retrieve it. I can run it the for loop in parallel. It will use the OpenMP to run the for loop, which is really cool for this one. And then on the Python level, I can run it. I can get the docstring. Everything is compatible. Same as Pybind11. So I have the implementations which require the Python list. So in Pybind11, it will automatically convert the Python list to the C++ vectors. So you don't need to handle those hassy things. And return now as a list. Within, I just put all the implementations same as the before. Then on the CPP file, I just bind this function to the explicit Python name. I can put the docstring. I can put the name of the variables in it. Meanwhile, I have another implementations. So the input is a little bit different. The input is the NumPy array and return out as the NumPy array. And what's the difference between I provide the Python list and the NumPy array is I have to access through they call the buffer info, the array underneath. Cython have the similar concept. It's called memory field. So I just access to the buffer info, and after those two implementations, I can bind to the same Python functions. Does it sound cool? It means if you have multiple argument lists, you can bind to the same Python method like this. If you put the NumPy array, you look at the NumPy array implementations. If you pass in the Python list, if you use the Python list implementations, if you have a different type of arguments on that, you look for that. The dot-string will also put all those different implementations dot-string together. So it is pretty cool for Pybind11 this way. And then go for the class implementation. I have the CPP source code, and then I can bind the class via the Pybind11. In Cython, there's a two-way doing that. One is you write a Python-like class, but before you declaring the class, you just put the syntax cdef in it. Or you can have your own source code of C++ imported in Cython level and also the class. It supports the property, class method, static method, everything compatible. It supports the operator overloading for both libraries. Inheritance, of course, is very important for object-oriented language. I would say they both support. For Cython, it supports in extension types, but not when you're importing them from the CPP files. Memory management, I would say, is the biggest difference between these two libraries. Is for Cython perspective, everything working well. It means if you have the objects, then the memory life is maintained by the garbage collector, by the Python, and also reference count. So in case, there's an exceptional case is if you have the pointer in the Cython, and you dynamically allocate the memory in it, then you have to declare the constructor called cinf and the destructor callocate, same as the CPP class in your Cython class to do it. Pybind11, it is called return value policy, but I will go through it after. So have a taste of Cython and Pybind code. So for Cython, it is pretty like the Python code. You declare the class, you have your dot-string, you declare your attributes, which is only accessible in C level. If you would like to expose it out, you can have properties to do it. Then I have another class called stop order, which has an extra attribute, which is called the stop price. So on the Python level, I create an object, the stop order. I can see the inheritance order within the stop order, which is the subclass of the order, and also I can access to the subclass attribute. On Pybind11, I have the source code, which is in header files, the same kind of implementations of order and stop order. Then I just bind the order class to the Python class name order. I put the dot-string. I just bind the constructor and also the methods. I can also have the subclass called stop order, but I have to declare the ordering, the inheritance ordering, which is the superclass is the order. Then I just declare the extra attribute of it. On the Python level, it works well. You can access to the subclass, the superclass attributes. You can have the inheritance ordering. You can have the dot-string. Everything is likely the same. The same way for Cython, you can import your header files in it. You can import the class and their methods. And second, you have to have your own Python class to wrap on that to contain the pointer, which is dynamically allocated memory on it. And you have to declare what kind of methods and attributes you would like to expose out. Everything is the same. This topic is, I would say, is sensitive because if you restart to write the C extensions, you may not want to have some access of the Python object or module. But in case you would like to, how you can do it for both parties is feasible. But in Cython, it is pretty straightforward. You just write the Python-like code, and Cython will determine which part it is in C level, which part is in Python level. But Pybind11, the same kind of implementation. So you have to get your Python object to use the method law attribute to call the methods out. After the operations, you retrieve the Python object. You have to cast it back to the C levels or the C types. And this is comparatively make your code a little bit harder to read. And finally, the biggest difference, return value policy. So if you have any experience of writing the C or C++ source code, then you know that memory allocation or the memory management is very critical in writing your program. So same as Pybind11, for example, I have a class called data, and I have a string contained in it. And meanwhile, I have a container contains the pointer of data and the method to return out the data pointer. Then I bind these two classes and also expose the method. On the Python level, I create the object of the container. First time, I get the data pointer out and print the value in it. It's working fine. But second, there's memory corruption. Why does it happen? So the main reason is by default, in Pybind11, they have the default return value policy to transfer your ownership of the object to Python. So the first time when the pointer is called, no one referencing it, print out, that's it. And then the garbage collector in Python will clean it out. The second time, you look in the same address, but the memory has gone. So it has the memory corruption. I would say this is the fortune case. It means most of the time, you just get your Python program crashed silently with segmentation fraud without any traceback and really hard to debug. The workaround is you provide the return value policy to explicitly tell the ownership maintains in CPP level. So you have to maintain the lifetime of the object in your C source code, but you have to handle it carefully, otherwise there will be a memory leak. You accumulate so much memory without freeing it. The smarter way is, why it's called Pybind11, why it is the lover for CPP developer, because it uses a bunch of C++ standard library 11. So you can get your share pointer. So if you're not familiar with that, share pointer is just contain the primitive pointer and also the reference count. It's quite similar concept as Python using the reference count and garbage collector. So once the reference count is equal to 0, then the share pointer will clean, we call the destructor of the object in the CPP level. So the method just returned the share pointer out without, or just specify the default return value policy. Then the reference counter will hold well for the lifetime between Python and C level, and everything works well. To wrap up, I would say between the two libraries, Cython is easy to write. So if you're a Python developer, you can write the Python-like syntax via the Cython. Pybind11 is quite modern, I would say, in these days. And people are more likely to move to Pybind11, especially you have your own C++ source code. And in the case that you have your open source project, if you start from there, it means you can claim your project is supportable for Python and CPP, which is cool. But there are much more considerations between the two libraries. For pragmatic cases, you have to see your resources, how much time you can afford to pay. If you have written the CPP before, you know that there's 2 or 3 times more development time in writing the CPP code. Whether you're migrating the Python code or you're writing it in completely new business from scratch. And your team expertise is pretty important, because if in your team no one has any experience of writing C, it's really hard to maintain in Pybind11. But if your concern to compare it is on the performance, I would say you just keep it aside. In my experience, most of the time, the performance is roughly the same. Pybind11 in some cases maybe a little bit better, but a little bit is not a lot. So going back to the 2 algorithms, the first one is the slower complexity. The second one is the smarter way of doing it. So on Python, because as mentioned, we are using different algorithms, different libraries to it, so it doesn't have the consistency on the labels count. But if you write it in Cython and Pybind11, everything analyzed. The better capacity will returns out the better performance. And between Cython and Pybind11, the performance I would say roughly the same. And compared to Cython, it already impressed your boss. Future perspective, I would say the world is now moving toward to Pybind11. There are several Cython projects, open source projects, which are requested by the users to move into Pybind11. For example, TensorFlow is migrating their string to Pybind11 in progress as well. And second is keep an eye on MyPyC. If you're a big fan of typing, then you have used MyPy already, right? So MyPyC is used to compile the MyPy, but it's not ready for production use, for general usage. But if it happens, it means in your Python source code, you just write all those typing, use MyPyC, compile to C extensions, and then I believe it will still a huge market from Cython. Recommended readings, I would say Dropbox brought this post, are generally to type checking 4 million lines of Python. It tells about history of the Dropbox team to implement the MyPy and MyPyC. So some of the considerations, maybe also your considerations of writing C extensions. Another one is the TensorFlow's proposal to migrate to Pybind11. They have listed out a lot of points of the pros and cons of MyPy and why they moved to that way. It also may be your consideration if you look into the Pybind11. Finally, if you would like to click on the link that I showed you before, I will upload the presentation materials lately in my GitHub account. If you have any questions, please don't hesitate to shoot me emailed. And is it all good for the time, or can we have the questions, Q&A?
Yeah, it's perfect. We only have like 2 minutes for questions.
Okay. If you have 2 minutes, can I thank you for the committee's work. It is a very great organization of the committee. So, any questions?
We are very pleased. So, thank you, Gavin. To me, you have announced another drastic change in TensorFlow. I'm afraid it's coming, right? Or?
It will be the implicit change inside, okay, so it will not changing the API or the prototype of it. They just change the current implementation of binding the C source code to Python wrapper.
Okay, I hope they would not forget the safe allocation. So, any questions? No. I'll be the one to run around.
Hi, so I'm a novice in the domain, but if I have a pure Python package in the open source domain, if I would start implementing some portion of this package in C, what is the implication of the packaging process for my package?
That's a very good question. I would say there's 2 points. One is it's not necessary to migrate your whole project to C extensions. In my case, for example, in my professional work, we just take the 80-20 rules. You just migrate 20% of your low-level API, break into small chunks, and then just do it in Cython. For the remaining, you can keep the Python code. So in the zap.py, I just put the PYX files you would like to compile, and then left all those remaining. And the second is, with those 80-20 rules, I would say choosing Cython and Pybind11 may not be a big concern, since you just migrate some piece of code to there. So it's more like the concern of whether you have the time and the expertise to maintain it.
All right, thank you. I'm afraid we don't have time anymore, but feel free to ask questions during lunch. Is that okay?
Yeah.
Okay.
That's good. Thank you.
Thank you, Gavin. This is your diploma. Thanks for coming.